Okay. So we're basically doing hitting the climax of the course, the theorem of the theorems of Ascoli-Arzelà and Stone-Weierstrass. Okay. So Ascoli-Arzelà is basically a compactness theorem, right? It says that under certain conditions, whenever you have an infinite sequence, you're guaranteed a convergent subsequence. Right, so that's so-called sequential compactness. But sequential compactness is equivalent to compactness in a metric space. So we are in the world of continuous functions on some set, right? So continuous functions on some set. In this case, K is compact, and we're wondering. And we have the metric on it. We have the, so this is given the sup norm metric. So this plus sup norm metric, this gives us a metric space. And our question is basically, what is compactness? What is compactness in this metric space? Okay. Now, of course, you know what compactness is, right? You can just say it's given any open cover that exists a finite subcover. But you'd also like to have something a little bit more usable than that. Like in Euclidean space, we have compactness is equivalent to being closed and bounded, right? That's an easy thing to use, easier to verify than the condition of compactness itself, right? And so you'd like to have something like compactness for this metric space of the set of continuous functions with a sup norm metric. And Ascoli-Arzelà gives you the answer to that. Okay, so theorem is this. Oh, and I mailed you a file this morning, a presentation from a conference about 14 years ago titled Ascoli-Arzelà and the Meaning of Life. So I hope that answers. I hope it will give you some sense of why people care about Ascoli-Arzelà. Right? It's it gives a couple examples of its application in something called the calculus of variations and also differential equations. So yeah. Okay. So yeah, and so next class, I think we'll just do homework problems, and then we'll also have, I think we'll have an extra class on Friday. We'll answer more homework problems. If people have questions about homework problems, I do have, sort of regrettably, I do have your homeworks to get back to you. I commented on the last one just to some degree, but yeah. So we can talk more about it on Wednesday and on Friday. Okay, and I'm happy to meet other times, and we can talk about homework as well. So if you want to have more sessions on homework, I'm willing to do it. Okay, so let me make sure I get things right here. F sub n, a sequence of complex valued functions on K. And if K is compact to the F sub n are pointwise bounded, and 3, the Fn, the family is equicontinuous, then you're guaranteed that the Fn are actually uniformly bounded on K, and 2, there exists a convergent subsequence. F sub n has a uniformly convergent subsequence. Okay, so yeah, so basically, maybe it'd be better to phrase it like this: K, a compact set. Let me write it like this. if you have these two conditions, right? If you have these two conditions, then you've got a uniformly convergent subsequence. Okay, so this is basically the condition equivalent to compactness. Okay, that your functions are pointwise bounded. Actually, anyway, roughly speaking, this is equivalent to compactness. Okay, so so here's the proof. Right. First thing we want to do is show that the f sub n are uniformly bounded. Right. So what we have is that we're on a compact set, and we know that at every point, right, at every point we have a bound, right? We have pointwise boundedness, right? So we know that at each, right, pointwise bounded means that, right, at each there exists like a m sub x for each x. Your compact set, right? So there exists some bound for every x, right? So pretending that we're in Rn, pretending that we're got complex value functions on some interval, right? There's some for each x there's some bound, right? So your function is bounded between, at that point, all the functions are bounded between these two things, right? So you've got bounds at every single point. Okay, right? And we're trying to show that that we actually have a bound. We have a bound that doesn't depend on x at all, right? Okay. So what do you think we're going to do? Anybody have an idea? So we've got k is compact. We've got pointwise boundedness, right? At every point you've got bounds. And we have equicontinuity, right? Equicontinuity, remember, means that your functions all vary in the same way, right? Like if you say, I want you guys to vary by less than 1. I want everybody to vary by less than 1. Then there's a delta so that as long as you take 2 points within that delta, the guys don't change more than one unit, right? Okay, so what do you think? We've got this compact set here, right? We've got this compact set here. We've got bounds at every single point, right? And we've got equicontinuity, which means that people don't move that much, right? Right? Everybody sort of like moves only a little bit, right? And we want a bound for the entire set. So any ideas? Let me start off with equicontinuity. So like equicontinuity, equicontinuous means, right, of course, given any epsilon, there exists a delta, so that if the distance between x1 and x2 is smaller than delta, then the difference between fn x1 and fn x2 is smaller than epsilon for all n, right? So for every single function, they don't vary that much, right? So think, right? Like maybe what we'll do, right? Let's fix an epsilon. Let epsilon be 1, say. Oops. Let epsilon be 1, right? So then we get this delta, get the delta. Yeah, and the delta for 1. Right? So that gives us these, we can cover every point with a delta neighborhood, right? And that will tell us that in that delta neighborhood, you're not going to vary that much from the center point, right? You're going to vary by 1 from the center point, right? At most, you're going to vary by 1 at the center point. Okay. Anybody see where this is heading? Got ideas? Yeah.
I don't know if this would be the next step, but at some point, are we going to take a finite subcover?
We'll definitely do it. Yeah. In fact, let's do that right now. Okay. So proof. So right now we just sort of like, brainstorming. Now let's actually write down the proof. So take epsilon to be 1, get the delta. So we know there exists a delta such that, of course, if the distance between x and y is smaller than delta, then the distance between fnx and fny is smaller than 1, right, for all n. Okay, so now cover K with delta neighborhoods. Right? Cover K with delta balls. Right? Every point you take, cover it with a delta ball. Right? Okay. Then, by compactness, K compact means that there exists some points, x1 through xk, say, such that the delta balls, the union of these delta balls, covers K. Right. Sorry to do this, but just need some space. Okay, so we cover the domain with delta balls, right? Okay, so now, and then we've got a finite collection of them. So there's like x1, x2, x3, x4, and x5, say, right? They're also, and we cover, and we take the delta neighborhoods around those guys, right? And the delta neighborhoods around those guys cover your whole space. Okay. Okay. So now, right. So we know that the functions don't move that much on the delta neighborhood, right? All the functions can't vary by more than, each function will not vary by more than 1 over that neighborhood, right? So let's use the second point. The Fn are pointwise bounded, right? So we know that at each of these points, there's a pointwise bound for everybody, right? So, Fn pointwise bounded means that there exists n1 through nk, right? That are bounds for the whole family at x1 to xk, respectively. Right? So at each point, we have an m, right? There's an m1 for this guy, there's an m2 for that guy, et cetera, et cetera, et cetera. Right? What are we trying to get?
There's just one bound for all.
There should be one bound. How do we get that one bound? I think you can do it. I believe you can do it. Natalie.
Do the maximum.
Take the maximum of those bounds, right? Let m be the max of the mi, right? And then, right, so you know that at each of those points, that m will bound the values of the functions at each of those points, right? Okay, but what about at the other points? We've got a bound at these finite points in here. What about some other point here, x? What about at x? Do we have a bound? What kind of bound do we have for there? Natalie, you're nodding.
That one's also, is it delta or is it epsilon?
It's delta away from, it's within delta of x1.
Okay, so then it's within epsilon of m.
Exactly, right? So this guy was within epsilon, within delta of one of these points, but we know that the function doesn't change by more than 1 to this point, right? So, right, then for any x and k, x must lie in some, x lies in some delta ball for like xi, some xi, right, for some I, right? Lies in one of the delta balls, right? So, right, so the value of fn at xi is controlled by the value at, the value at x, the value at x is controlled by the difference, that plus fn xi minus x. Right. No, plus fxi, plus fn xi. Right? I'm sorry, equals that. Right? Now this thing, I should have written it backwards. Sorry, let me put the minus sign here and the plus sign here. Okay. Well, this thing is controlled by 1, right? This thing less than or equal to this plus this, right? This thing is controlled by 1, and this thing is controlled by capital M, right? And so, you know, whatever function we have, whatever point we have, they're all controlled by M plus 1. Make sense? Sort of. I hope that makes sense, right? Right. We find there's only finitely many points here, and so we can take, you know, we can find a bound that controls, you know, because of the pointwise boundedness, the maximum of those bounds will bound all the functions at these points, right? Then, you know, by equicontinuity, you know, these guys were the centers of delta balls, right? That covered the set. So if you take any point in the set, it must lie in one of those delta balls, right? Lies in one of the delta balls. What meaning? If you're in the delta ball, that means that you're right. If you're in the delta ball, that means that your values don't vary by more than 1, right? So the difference between your value here and the value at the center point can't be more than 1, right? And so you say, oh look, well, the value at the center point is controlled by M. So the value here must be controlled by M plus 1. Okay. Okay, so the second part is to show that f sub n has a uniformly convergent subsequence. Okay, you know, Huang, I'm afraid maybe let's take the picture now and then get back to it. So you're gonna watch the video later. Okay. So yeah, if you guys don't mind, come up to the board. We'll take a class picture, or we can go outside. Which is better?
You can go outside today. It's very pretty.
It's very pretty day. Okay, let's go outside. Step outside. Okay. So now we want to get to the real part, which is showing that it has a uniformly convergent subsequence. So part 2. It exists a uniformly convergent subsequence. Okay, so we use a fact. And this was actually something that I believe I put in your homework early on when we were doing compactness. So K compact implies that there exists a countable dense subset, which we'll call E. Okay. So whenever you have a compact set, you can create a countable set inside of it, and that set will be dense. The way you do this, let me sort of sketch it out. You say, well, look, I've got a compact set. I'm going to cover everybody with neighborhoods of radius 1 over radius 1. Okay. Then I can take a finite subcover, so I'll have finitely many points, right? And everything inside here is within one of those points, right? And then you do the same thing for 1/2, right? And you get a bunch of more points, right? And you know that every point inside K is within 1/2 of one of those points, right? And then you do for a quarter, and et cetera, right? And in that way, at each point you get to generate a finite number of points. So the points altogether are a countable set, right? And you can get, in that way you can get points that are infinitely close to any point. In other words, the union will be dense in K. That's basically the proof right there. Okay, so maybe just notice that if you have a compact set, then there is always going to be a countable dense subset. Okay, so now recall we had this theorem the other day that said that if you have f sub n pointwise bounded on a countable set, then there exists a pointwise convergent subsequence, fnk, right? We proved that last time, I think. Using basically Cantor's diagonal argument, right? We created these guys that converged, and then we took the diagonal sequence, and then that converged on every single point, right? Okay. So okay. So the claim is that so those guys converge, and the claim is that in fact those guys converge uniformly. Okay. Converge uniformly. Okay. That pointwise convergence subsequence, because of the compactness and because of the equicontinuity, are actually going to converge uniformly. Okay. So let's prove that. We want to show that there exists an epsilon. No, we want to show that given an epsilon, there exists some number, and such that if K and L are bigger than N, then F and K x minus F and L x are smaller than epsilon. Right. We want uniform convergence, so this is going to be at every point in K. Okay, and as before, we have equicontinuity. So let's see. Yeah. So by equicontinuity, we know that there exists a delta such that if the distance between 2 points is smaller than delta, then the distance between any of these guys is smaller than epsilon over 3, right? For all K. So everybody in the subsequence, I mean everybody in the whole family, frankly, but a priori, everybody, no, a fortiori, stronger than that, everybody in the subsequence certainly satisfies this. Okay. Okay, so, okay, so, okay, so we're going to play kind of a similar game. We'll say, well, look, look, we cover K with delta balls again. Okay, but this time we're going to center the delta balls on points of E. Okay, we're not going to cover every point in K. We're only going to cover the points in E, but that's enough because because E is dense, we're still guaranteed that we're going to cover K. Right, right. The points of E are dense in K. Whenever you cover them with delta balls, every point is within delta of one of those points. Right. Cover with delta balls centered at points of E. Okay. So by the density of E, these delta balls, cover K. If we take the union of all the delta balls at points of E, over all points of E, that will cover K. Okay. Again, we'll pull out compactness. We say, okay, now K compact implies that there exists a finite collection E1 through E. I call it EP. EP in E, such that the union of the balls, the union of the delta balls from I equals 1 to P still covers K. So we've got a finite cover here. Okay. Okay. Oh, okay. See you. Watch the video. Okay. Everybody all right? Okay. So remember what we're trying to show, right? We're trying to show that we have uniform convergence, right? We're trying to show that we have uniform convergence. In other words, that we can get all these guys uniformly close to each other. Okay, right? That given an epsilon, we can find a time past which all pairs are within epsilon tubes of each other. That's the Cauchy criterion. Okay, right. And right now we're just sort of throwing in first equicontinuity. We cover the space with delta balls, right? Cover the space with delta balls. We end up with a finite subcollection E1 through EP, so that the delta balls of this thing cover our original set. Okay. We want uniform convergence. Okay. Okay. So now we say, well, look, just consider these points here. Consider this set, E1 to EP. Okay. We have pointwise convergence. Right? We have pointwise convergence for each at each point. Right? So, right, for each of these points, given an epsilon, we can get everybody within, we can get everybody close to each other at that point. Okay. And there's only finitely many of them, right? So, since there are only the E1 to EP are finite, we have uniform convergence. On just that collection. Right? Because remember, uniform convergence means that we can choose the n independent of the point. But there's only finitely many points. So for each one, we find an n, and we just take the maximum of those guys. Is that clear? You guys getting this? Right. Right. Pointwise convergence means that Fn, k converge pointwise. Converge pointwise at EI means that given any epsilon, there exists an n such that if k and l are bigger than n, then f and k ei minus f and l ei is smaller than epsilon, right? But we can do that, we have that for every single point, and there's only finitely many points. So take the maximum of the n, and that maximum n will work for all points, right? All of the ei. Okay. Right. So, okay. So that gives us uniform convergence on these guys. Is it making sense? Ask a question if it's not making sense. Yeah, sure.
I'm a little confused
Yes.
about how we can say that the difference between, at a certain point of two different subsequences. Oh, wait, never mind. Actually, that makes sense. Never mind.
Yeah, this is
Because that's the definition of
pointwise
yeah.
convergence. That's what pointwise convergence means. And maybe it's clear if I say there's an n depending on I. Right? So, right, converging at EI means that given any epsilon, there's an n sub I, such that as long as you're past n sub I, then these guys are within epsilon of each other. Right? We know that's true for each I, right? So since there's only finitely many i's right there, right, just from 1 to p, right? So let n be the max of n1 to np. Then if k and l are bigger than this maximum guy, then fnk ei minus fnl ei is smaller than epsilon at every ei when I equals 1 to p. Right. So we have uniform convergence. Okay. Okay. So remember, so so we have uniform convergence, right? So choose n such that k and l bigger than n implies that the distance between fnk ei and fnl ei is smaller than epsilon over 3. All right, for I equals 1 dp. Okay. Okay. So this thing here was just to show that pointwise convergence implies this thing here was basically just expanding this thing here. Okay. So what I wrote here, I'm just now going to erase. Okay. Okay, so remember what we're trying to show we're trying to show that there exists a time past which all of these guys at every point in K, right? Right now, we have uniform convergence, but only on these center points, right? We want to have uniform convergence at every point on K, right? But we have it. Okay, so now for any x in K, what am I going to say? I think you should. I think you can do it. This is kind of my dream that by the end of the course I'll be like, what happens next? Okay, you can do it. You can do it actually. Given any point in K, right? So here's our K, right? We have these sort of magic points, right? E1, E2, through EP. We have uniform convergence there, right? Each of them is enclosed in a delta ball, right? The union of those delta balls covers all of K. Those deltas are chosen, those deltas come from equicontinuity, right? We have uniform convergence on their centers, right? Now we choose some random point, x. Either I'm excited or it's all confusing. Yes, Anne?
Well, since x is in K, isn't it enclosed in one of the delta?
Yes. So we know that x lies in some delta ball for some I. Right. There's got to, u lines one of the i's, right? And remember what we're trying to show. Yeah. So we're within. We're close to, right, here's our x, and here's our e sub I, right? We're close to e sub I. How does that give us what we want? Right? Remember what we want. We want an n, we want to see that these guys are close to each other, right? Consider now f n k x minus f n k, f n l x. And
Could we like slide in an FNKEI?
exactly, right? We're going to slide in the f and k ei's, right? So we'll subtract it off, and then we'll add. We'll subtract it, and we'll also add it, right? So this is the same thing as fnxk minus fnlk, fnlx, sorry, fnkx minus fnlx. We are going to subtract. We're going to subtract fnkei plus fnlei, but we also need to add it on fnkei minus fnlei. Okay. The usual trick, right? And now, how are we going to sort of split this term up? Right? We want to rearrange things. What should we pair? What should we couple? What do we have control over? Yeah, sure.
We have control over the subsequent, like the f n sub k by equicontinuity.
Yeah, by equicontinuity, we know that for everybody in the sequence, as long as the points are within delta of each other, the values are within epsilon over 3 of each other, right? So let's look here, this guy minus that guy, right? X and EI are within delta of each other. So we know that this thing is going to be small, x minus fnk ei. That's a good thing to pull out. What else do we want to pull out?
Can you do the same thing for the L?
We do the same thing for the L because it's true for everybody, right? So we get fnlx minus fnlei. And I've changed the sign, that's okay, because multiplying by -1 is okay, since we're taking the opposite value. Right? That thing's small, and then what's left? Right? We got this thing minus that thing, right? And then what we have left is just fnk ei minus fnl ei. Right? Okay, well, that thing is smaller than epsilon 3 over 3. That thing is smaller than epsilon over 3. And what about this thing? fnk ei minus fnl ei. You know it's smaller than epsilon over 3. Why? Why is it smaller than epsilon over 3?
Because of pointwise convergence. It's whatever we've heard over there.
That's what we're trying to get. That's what we're trying to get. So that's not, you can't use that. Because of, right? And?
Is it because we have uniform convergence?
Because we have uniform continuity, right? I mean uniform convergence, excuse me, right? We had uniform convergence, remember we had uniform convergence on those finite points. This is just one of those finite points, right? So since our n is big enough to ensure that these guys are within epsilon over 3 of each other, this thing is smaller than epsilon over 3. And that's the end. Okay, so that's the proof of Ascoli-Arzelà. Okay. I'm a bit torn because we did not get to the proof of Stone-Weierstrass, which is also a super, super important and kind of cool theorem to prove. So, well, see you guys on Wednesday.
Do you have a video from previous?
I do. So maybe we can you guys can watch the video. Although it's probably better if I explain it to you directly, but you can watch the video and we can do homework problems on Wednesday. Sounds good. Let's do that. Okay. Yeah, Stone-Weierstrass basically says that you can approximate any continuous function uniformly with polynomials. That polynomials, right? We've just shown what compactness means in the space of continuous functions. Stone-Weierstrass says, what is a dense subset of this space? It turns out polynomials are a dense subset of this space, which is an important fact. But even more important is the technique, which is something called approximation of the identity. So that's like both the fact and the proof are really important in analysis. I'd say the proof, the technique used in the proof, even more so than the fact itself. Okay, so yeah, watch the video. Okay, see you guys next time.